Okay, so in the previous 2 weeks, in the previous two, I guess, lectures, we talked about some graph algorithms. So in the first lecture, we talked about like basic ones like BFS, DFS, DSU. The second lecture, we talked about Dijkstra's, Floyd-Warshalls, how to deal with weighted graphs, stuff like that. Today, we're going to be talking, continuing that. Probably going to be our last talk about about graphs. But today we're going to talk about trees, some basic properties of trees, and how to essentially solve tree problems, and a special tip about trees. So, yeah. So, trees. What are trees? Well, trees are a special type of grass. So, a tree has to be connected and has no cycles. So a tree, like for example, like if you have two nodes which are connected by an edge, that's considered a tree. But if you have three nodes that aren't connected by any edges, that's not connected, so it's not called a tree. In fact, a graph, which is just a bunch of trees that are not connected, that's considered a forest, or basically a bunch of different trees. So trees have many basic interesting properties. So like for example, the first property is there exists a unique shortest path between any pair of nodes. Also, they have exactly n minus one edges. And this is actually relatively easy to prove because if you consider the number of connected components, every time you add an edge and don't form a cycle, you're decreasing the number of connected components by one every time. And so uh, at the end, you're going to have one connected component in total. So there is n minus one edges because you're getting rid of n minus one connected components. Additionally, trees are bipartite, which essentially means you can split them into two groups such that there aren't any edges between each group. And there are other very, very nice properties of trees, which we won't talk about. And there are many very cool ways to utilize them. But so I kind of wanted to say this, but tree problems are generally very difficult. Like if you go on code forces and then you type the tags like tree and DFS or something like that, all the problems that you get are basically all going to be 2000 plus. So trees are actually a very difficult problem topic, but I'll try to introduce them a basic way, like as basic as possible. So the property of trees that we're going to talk about today is the fact that there exists a unique shortest path between any pair of nodes. And this is actually it's a very powerful, it's a very powerful property of trees that a lot of problems use. And we will talk about how to solve problems that ask you for shortest paths and stuff like that. So yeah. Um, so while BFS and DFS can be relatively quick on some shortest paths, like for example, if you want to find the shortest path from one node to every other node in a graph, well, okay, you can use BFS or DFS. That'll be able to do a lot of calculations about shortest path on a tree, right? But because let's say you're doing queries where you have a bunch of different paths that you want to find the shortest path, or you want to find what the shortest path is between A and B, where A and B is like a bunch of different queries. DFS and DFS might not be the best way to do it. Floyd-Warshall or Dijkstra's won't help either. Dijkstra's only helps with weighted graphs. Floyd-Warshall is n cubed, which means it won't be applicable for most problems where n is 10 to the 5. So first so instead of using any of those algorithms, let's first try to develop a new algorithm to be able to find the shortest path on the tree. After all, we know that the shortest path is unique. There only exists one path from A to B. So let's quote unquote root the tree at node 1. So how we would root this tree is instead of having like normal edges and stuff, our root is like the root node of the tree. And then every edge going to the root, like every node with an edge going to the root, we say that the parent of that node is the root, and then the parent of its children, and then if you go further into its children, then you say that the parent of those children are that, and so on and so forth. So we can say something like that. And so if we look at the structure of the tree now, if we write the root at the top and then the first layer, and then the second layer, and then the third layer, we'll realize that it actually goes up from a point A up until it reaches a particular node, which is a very special node. We'll talk about that node later. It's called the least common ancestor. And then it'll go from that node all the way back down to B. So it'll go from A, it'll go up the tree, up until it reaches a special node called the LCA, and then it'll go back down to B. So that is the shortest path from A to B. So let's call the special node the LCA. If we can quickly compute this node, it's actually very easy to effectively answer many shortest path queries. For example, if we wanted the shortest path, then we can pre-compute the depth at each node, and then we would just be able to say depth at A plus depth of B minus 2 times the depth of the LCA, and that would very easily tell us what the shortest path between two nodes A and B is. So how will we find this LCA? Well, let's talk about that. So there are two methods of finding the LCA. There's one method, which is Euler-Tor plus any type of range minimum query. So if you use a segment tree, then that'll allow log n queries. If you use a binary index tree, that'll allow log n queries. But if you use, or I don't think you can use a binary index tree, but if you use a sparse table, it'll actually allow for O of 1 queries. So this method allows for O of n log n pre-computation and O of 1 queries, which is actually technically strictly better than binary lifting. But because that requires prior knowledge about like sparse tables and stuff like that, we'll stick to binary lifting for now. So binary lifting is n log n log n, but it's a lot easier to implement than the Euler-Tor and ARM-Q method. And it's also it's also more fun to code, I guess, at least in my opinion. So we'll be talking about binary lifting. So the idea behind binary lifting is as follows. So there are 2 steps. The first step is for each node, you calculate the 2 to the kth ancestor of that node. So for every k, you calculate, or for every node, you calculate what is the ancestor of that node, what is the ancestor of that node, what is the 4th ancestor of that node, the 8th, the 16th, the 32nd, ... And the second step will kind of explain why we want to do that. And now, after we're able to pre-compute all of that, there are n log n values there. So if, we should be able to pre-compute it in n log n. The second step is to use those values to calculate the LCA between 2 nodes. So we're using those values. This is actually where the term binary lifting comes from, but we're essentially using those like 2 to the k values, and we're essentially using binary lifting to lift all of our nodes to the LCA. So first, let's talk about how to do the first step. So to do the first step, it's actually the easy part. So first, we can find the single parent of each node using a simple DFS. So we root the tree at an arbitrary node. Usually it's node 1. Then we run a simple DFS. We start from 1, and then we can essentially keep track of the parent within our DFS. Whenever we reach another node, we just set the parent to the value that we came from. So yeah, so finding the parent is just a simple DFS. After that, we use the following formula. So if ank ik is the 2 to the kth ancestor of I, that means that ank ik plus 1 is equal to ank ik of k. What does that mean? Well, if you take the 2 to the kth ancestor, right, and then you take the 2 to the kth ancestor of that, you'll get the 2 to the k plus ancestor. So it's actually a pretty neat trick to be able to pre-compute all of the 2 to the kth ancestors. So we can just simply use a loop. We can use this formula and just a simple loop, and we'd be able to pre-compute all of the entire ank array in O of n log n. So this is actually a pretty nice trick to be able to pre-compute the 2 to the kth ancestor of every node. Now, this is the hard part. So the binary lifting part. So the basic idea of binary lifting, it's if you understand what binary search is, it's kind of not really, but kind of similar. But basically, you keep taking the largest power of 2 from the quantity until the quantity becomes 0. So for example, if we wanted to take the kth ancestor of a node, we would take the largest power of 2 less than k, and then we take the ancestor of the node, and now the ancestor that we take it to is k minus 2 to the like largest power less than k, which is less than the 2 to the power of that number. So every time we're reducing the power of 2. So at most it's O of log n. So this is the general idea. So we're gonna want to try to apply this onto our actual problem, which is finding the LCA. So first, we want to make the vertices the same depths. This the reason for this will be explained by the second step. But essentially, we want to make the vertices the same depth by just comparing the depths. So we essentially do binary lifting on the difference between the two depths. So every time, as long as the power of 2 doesn't take the node above the other node, then you take, and above in this sense is just like lower depth. So if one of the nodes has a higher depth, then you use binary lifting to get them to the same depth. After that, we use binary lifting as long as the ancestors are not the same, or as long as the nodes themselves are not the same. Well, yes. So, for example, if you take the 4th ancestor of a node and that makes the nodes the same, then you stop doing that, and then you don't do that. Then you take the 2nd ancestor, let's say that makes them different, then you do that, and then after that you take the 1st ancestor. If they're still different, then you go there, and then after that you'll end up with 2 nodes with the same parent, and the parent of those 2 nodes is going to be the LCA. So essentially the basic idea behind this, and it's like kind of the reason we want them to be the same depth, is because once we get them to the same depth, we just compare the 2 nodes and make sure the 2 nodes are different the whole time. And so because they're at the same depth, as long as they're different, that means that they're still both in the subtree of the lowest common ancestor. So you can keep going, and then you can use binary lifting. So it's actually a pretty neat way to find the LCA. Yeah. So now I'll talk briefly about how to use LCA to solve problems. So LCA is very powerful to solve, can characterize the whole A to B. So because you just go from the vertical path from A to the LCA, then from B to the LCA. So there's a lot of ways to take advantage of this to be able to solve tree problems. So for example, if you want to use prefix sums, you can actually do that with LCA, because when you're updating a path, you can just split the path into 2 and then update both sections of that path. And then using that, you'd be able to do prefix sums. Another example is, let's say you wanted to do like queries, some sort of queries where it's easy to combine the 2 answers, and you can use prefix sums. Well, then you can just query for both vertical paths and then sum those together, and then you get the final thing. Another thing you might think is, oh, well, what about path updates? Path updates also become really easy because you can split it into 2 vertical paths. Vertical paths are a lot easier to deal with than normal paths. And so this is actually a very powerful way to like solve tree problems. But the thing about this is LCA can only take you so far. There's some problems that you just can't do with LCA, maybe because vertical paths aren't sufficient. Like even if you decompose it into vertical paths, you're still not fully able to solve the problem, or maybe because it's very hard to combine 2 vertical paths or something like that. And so in that case, there are actually other algorithms that use LCA to maybe not decompose the path queries, but at least be able to figure out what the path queries are. And these algorithms are like, for example, heavy light decomposition, centroid decomposition, stuff like that. That those can take advantage of the properties of the LCA to be able to solve problems in a very efficient manner. So for example, HLD actually kind of is very similar to LC, or the idea behind heavy light decomposition is actually to solve a strictly harder version of the problem that LCA is trying to solve. So if you're able to find the LCA, like let's say using binary lifting, and then you want to do a path query, sometimes you might not be able to do that because you can't use like prefix sums or something like that. You need to use a segment tree. Well, if you want to use a segment tree, HLD is essentially just like an extension of LCA onto like segment trees, essentially. So the basic idea is you want to sort the edges into heavy and light. So the heavy edges are the edges that lead to like the biggest subtree, and the light edges are the edges that don't lead to the biggest subtree. And so what ends up happening is there's a way to prove that in any path and any vertical path, it actually only traverses long light edges. So we're actually using LCA to decompose it into two vertical paths. But this time, instead of solving the problem after finding the vertical paths, we can actually decompose those vertical paths further into different segments within our segment tree. And so actually HLD will allow us to do any type of path query within O of n log squared to n. I encourage you to do some more like research about HLD if you have the time to do that, or if you want to do that. But I won't go too in depth about HLD for now. So yeah, I've actually prepared some problems. Like I don't have the solutions and stuff written, but I would say like try or I'll go over the third problem. So if you look at the third problem, it's it looks like this. But like if you're looking at the recording, you can pause, or after you watch this, you can pause and read the problem. But essentially, I'll go over the idea behind the problem. So the problem is basically asking you to find how many paths have so for each max, or for each number, how many paths have have a max equal to that number. And the idea here is that in order for a number to have a path that the max, like the so in order for a number to be the max of a path, all of the numbers less than or equal to that number, or all of the numbers less than that number, would have to be on a single path. And so we can actually just keep track of two numbers, A and B, and then whenever you add another number to that, you can basically check, okay, well, A and B, is that number on the path from A to B? You can use like LCA to do that. So if the so so like for example, if you have two nodes, or if you have two nodes, A and B, right? And then you wanted to add a node C to this, right? You want to check if C is on the path from A to B. Then what you can do is you can take the pairwise LCA. So you take the LCA of A and C, you take the LCA of C and B, and you take the LCA of A and B. And so what this does is say if the LCA between A and B is equal to A or is equal to B, that means that A and B are on the same vertical path. So that means there's a vertical path from A to B. And so that means no matter where C is, as long as C is not like this, as long as C doesn't look like that, so if C is here, or if C is up here, or if C is up over here where it's like this, or if C is down here, in all of those cases, C is valid. But only in the case where this is true, C is not valid. So what we would do is we essentially case work. So if A is the LCA of A and B, then we take the LCA of B and C. So if the LCA of B and C is, let's say this value is L, right? L. Now we can check if the LCA of A and L, or okay. So if L is equal to B or L is equal to C, then we know C is on the path, right? But if L is equal to or if L is also if L is equal to A, then we're also done, right? But if L is not equal to any of those, we take the LCA between L and A. And if that is equal to A, then we're done because we know that it can't be possible. It's not on the path. But otherwise, we know that it is on the path. So yeah, and then we can do some more casework. Like now we can do like C and B, and then we can do all of this sort of stuff. And we so like let's say A and B are not on a vertical path, so the LCA of A and B is not equal to A, then you can essentially have a node C, like you can test the LCA between C and B and the LCA between C and A. If then so basically if like you can essentially like kind of like draw like a triangle. So then now you can casework, where is C? So if C is here, then it's on the path. If C is here, then it's not on the path. If C is here, then it's on the path. And if C is here, then it's on the path. And then you can essentially use your LCA to continually just like casework C, and then like, let's say that's not enough. So you want the LCA of A and B to be L. Okay, so okay. So now if the LCA of C and L is not L, that means that C is not on the path. And then okay, then if the LCA of C and B is equal to C, then C is on the path. Then if the LCA of C and A is C, then C is on the path. And if the LCA of A and C is not L, not A, and not B, that means that C is not on the path. If the LCA between and then basically that's the idea. You just keep caseworking and using LCA to be able to figure out whether it's on the path or not. And once you're able to do that, you can essentially say well, once you have A and B, right? You know that the path from A to B, so the path from A to B contains every single number from 1 dot 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 to I. So that means that the number of paths that go through or the number of paths that have a max of at least I plus 1 is size of A, like the size of the subtree of A, times the size of B. So this is the number of paths are, or yeah, this is the number of paths that have max at least I plus 1. And once you figure that out, you can use a simple manipulation to be able to figure out what the actual answer is. So yeah, this is just a neat illustration of not using LCA for path queries in particular, but using LCA to be able to figure out whether 3 nodes are on the same path. Using LCA to figure out whether like 3 nodes are in the same subtree or whatever. Like LCA can be very, very, very powerful if you use it correctly. So yeah. And I would say out of the 2 USICO problems, the ones that I didn't go over, the second one is definitely slightly harder than the first one. So I would assume I would recommend that if you want to try out LCA, you try to think about the first problem, think about how you would try to use LCA on the first problem. The official solution actually doesn't use LCA because LCA is technically not within the goal topics. But if you use LCA, it makes life so much easier. So yeah. Uh, yeah. And otherwise, yeah, that's it. So yeah.